Without warning, a wave of headlines rippled through defense and aerospace circles. The United States had quietly conducted a hypersonic test that left even seasoned experts speechless. Whispers of speeds reaching beyond Mach 10 surfaced, 10 times the speed of sound. What made the event even more mystifying was the cloak of secrecy that surrounded it. No flashy press releases, no pre-test fanfare. Just a test, a blur of motion, and stunned silence from those watching closely. Many believe this marks a breakthrough linked to the highly classified SR-72 Darkstar program, Lockheed Martin's long-rumored successor to the legendary SR-71 Blackbird. But insiders suggest what was tested may go even further. Faster, higher, more versatile. Whatever flew that day didn't just push the envelope, it shredded it. This test wasn't just a display of raw speed, it was a statement, a signal that the US has not only re-entered the hypersonic race, but may have just jumped several steps ahead. As tensions mount globally, and adversaries like China and Russia boast of their own hypersonic advances, America's sudden silence breaker couldn't have been better timed. From military superiority to global surveillance capabilities, the potential applications of a Mach 10 capable vehicle are as wide-reaching as they are formidable. And if this test is any indication, the dawn of a new era in American air dominance has already begun, quietly but unmistakably. The Cold War origins of hypersonic flight. Long before today's sleek prototypes and AI-assisted testbeds, hypersonic flight was born in the white-hot forge of Cold War rivalry. The 1950s and 60s saw the United States and the Soviet Union locked in a technological arms race that stretched from the ocean floor to the stars. It was in this fevered atmosphere that the idea of hypersonic flight, traveling at speeds exceeding Mach 5, first captured imaginations. Back then, one aircraft stood as the crown jewel of American ambition, the North American X-15. Rocket-powered, razor-edged, and perilously experimental, the X-15 reached speeds of Mach 6.7, well over 4,500 km/h. But it was never meant for long-range missions. Its fuel-guzzling engines and extreme heat limits confined it to short bursts of glory. The dream was alive, but the technology simply wasn't ready to support it. As the space race moved to center stage, hypersonic flight faded into the background. Researchers couldn't solve the twin challenges of efficient propulsion and durable materials. So, the dream of ultra-fast travel was shelved, filed away for a more advanced future. That future has arrived. The lessons learned from the X-15 and the decades of data since have finally matured into actionable design. With modern materials, computer simulations, and AI-driven control systems, what was once theoretical is now practical. The Cold War may have planted the seed, but the current era is bearing the fruit. What we're seeing now isn't just a revival of hypersonic ambition, it's a renaissance built on legacy, propelled by innovation. Enter the Scramjet, the game changer. The biggest bottleneck in early hypersonic efforts wasn't speed, it was how to maintain it without burning through fuel in seconds. Enter the Scramjet, short for supersonic combustion ramjet. Unlike traditional rocket engines that carry both fuel and oxidizer, scramjets inhale atmospheric oxygen at incredibly high speeds, igniting it with onboard fuel to produce sustained thrust at hypersonic velocities. This engine design flips the script. By using the air around it instead of lugging massive oxygen tanks, a scramjet becomes exponentially more efficient, especially at its speeds above Mach 5. In terms of specific impulse, a measure of engine efficiency, a scramjet can more than double what traditional rockets can deliver. More thrust, less weight, and greater range, the holy grail of hypersonic propulsion. Scramjets represent a critical leap not just for military applications, but for the future of aerospace itself. They open the door to ultra-fast transcontinental travel, next-gen surveillance platforms, and weapon systems that can strike across the globe in minutes. And because they don't need rocket boosters past initial launch, they can potentially be integrated into reusable aircraft, one of the most elusive goals in aviation history. What was once confined to academic journals and wind tunnel tests is now moving toward the runway. The Scramjet isn't just a concept anymore. It's a cornerstone of tomorrow's flight systems. And as America's new prototypes take shape, powered by these revolutionary engines, the horizon of what's possible is expanding at Mach speed. Why most hypersonic planes can't be reused. Yet as thrilling as hypersonic breakthroughs may be, there's a sobering reality that keeps engineers up at night: the reusability problem. The faster you go, the hotter things get. And at Mach 5 and beyond, friction with the atmosphere turns the surface of a vehicle into a firestorm. Temperatures can soar above 3,000 degrees, melting or weakening most known materials within seconds. So, while hypersonic missiles are already operational, building an aircraft that survives flight and comes back ready for reuse, that's still the mountain to climb. The core issue lies in propulsion and thermal durability. Scramjets, for all their brilliance, can't operate from a standstill. They need to be accelerated, usually by boosters or traditional jet engines, before they can even kick in. This complicates launch logistics and adds weight. Then there's the skin of the vehicle. The materials must endure temperatures hotter than lava without degrading. Currently, many components char, warp, or outright disintegrate after a single flight. That's why today's hypersonic vehicles are often disposable. They're weapons, not aircraft. Reusability, like we've seen with SpaceX rockets or the space shuttle, remains elusive in the hypersonic domain. But the tide is beginning to turn. New material science, hybrid propulsion systems, and rapid prototyping are bringing reusable hypersonic planes closer to reality. Companies like Hermes are leading the charge, chasing the goal of a plane that doesn't just fly once, but flies, lands, and flies again. It's the last great barrier before hypersonic aircraft go from concept to commonplace. And if America can solve it first, the skies will never look the same again. Chimera engine, the hybrid that changes everything. If there's a single breakthrough that could finally crack the code on practical hypersonic flight, it might just be the Chimera engine. Developed by Hermes, this revolutionary propulsion system is named after the mythical beast, and for good reason. Like its namesake, Chimera is a fusion of multiple forms, blending turbojet and ramjet technology into a seamless, adaptive engine that changes modes mid-flight. This adaptability is everything. At takeoff, the Chimera behaves like a standard jet engine, pulling in air and burning fuel just like the engines on a commercial aircraft. But as speed builds and the conditions shift, it morphs, transitioning smoothly into a ramjet configuration capable of handling supersonic and hypersonic speeds. This dual nature solves a critical problem: how to launch from a runway and still reach Mach 5+ without staging or boosters. The implications are enormous. No more heavy rocket assists, no more limited launch windows, just a sleek aircraft that takes off like a jet, accelerates like a missile, and returns like a plane. It's the kind of engineering leap that turns science fiction into aerospace doctrine. Chimera's design is also modular, allowing it to be tested across multiple platforms. This means rapid iteration, easier upgrades, and a shorter path from prototype to production. And with each successful test, the engine brings the US closer to a future where hypersonic flight is not just achievable, but repeatable. It's no exaggeration to say Chimera could be the engine that powers the next age of American flight. The Quarterhorse, a prototype built for speed. Every revolution needs its workhorse. For the US hypersonic resurgence, that aircraft is Quarterhorse, a name that evokes speed, agility, and raw performance. Developed by Hermes, Quarterhorse Mk0 was built in just 6 months. That kind of speed is unheard of in aerospace, where new aircraft often take years just to leave the drawing board. Yet, despite its rapid development, Mk0 passed every test it faced. Ground trials, structural stress tests, and simulated high-speed runs all confirmed what its designers had hoped. This aircraft wasn't just fast to build, it was built to be fast. The Air Force took notice, and quickly Mk1 was greenlit. By 2024, Mk1 was conducting taxi tests at Edwards Air Force Base, powered by an afterburner-equipped engine that hinted at its blistering potential. And it's only the beginning. Mk2 and Mk3 are already in development, with designs aiming to achieve fully autonomous supersonic flight and eventually hypersonic capability. Quarterhorse isn't just a prototype, it's a platform, a flying laboratory where new engines, new materials, and new control systems can be tested and refined in real-world conditions. Its rapid production also reflects a broader philosophy shift: agility over bureaucracy, speed over spectacle. In a world where speed is both a tactical advantage and a symbol of progress, Quarterhorse is racing to redefine what's possible. And with each new version, the U.S. edge in hypersonic flight grows sharper. Darkstar Reimagined, the next evolution in hypersonics. From the ashes of the legendary SR-71 Blackbird, a new vision is emerging. One not just faster, but smarter, stealthier, and more boundary-breaking than anything before it. The SR-72 Darkstar was once only a concept, a whispered possibility in Lockheed Martin's Skunk Works pipeline. But now that vision is being reimagined and brought to life by companies like Hermes, backed by military interest and a renewed urgency to dominate the skies once again. This new Darkstar isn't just about shattering records. It's about reshaping the very nature of air superiority. While the SR-71 peaked at Mach 3.3, the next generation craft aims to leave that in the dust, pushing towards speeds that edge close to space itself. Designed to fly at altitudes above 85,000 feet, this aircraft will practically skim the edge of the stratosphere, well beyond the reach of current air defenses and conventional radar. But speed and altitude are just part of the story. The real innovation lies in autonomy, AI-guided decision-making, and the fusion of intelligence and speed. Surveillance, strike, and reconnaissance missions that once required fleets of aircraft could now be conducted by a single platform, faster than any response the enemy can muster. This evolution of Darkstar is more than a leap in performance. It's a shift in doctrine. No longer reliant on brute force or sheer numbers, the future of air power lies in hyperspeed precision, adaptability, and survivability. And as the U.S. Air Force and private innovators continue refining this platform, it's becoming clear that this won't just be a successor to the SR-71. It will be something entirely new. A machine that doesn't just fly faster, it changes the game altogether. Building an aircraft that survives fire. The promise of hypersonic flight often collides with a brutal reality. The sky at Mach 5+ is an inferno. Friction between the aircraft and atmosphere at these speeds generates temperatures as high as 3,100 barum, hot enough to melt aluminum and warp steel. Surviving those conditions isn't just a technical requirement, it's a prerequisite for the very future of reusable hypersonic vehicles. That's why the materials science behind this new era of aviation is as revolutionary as the propulsion systems. Hermes and other leading-edge firms are working with exotic materials like titanium alloys, nickel superalloys, and carbon ceramic composites to build frames that don't just resist heat, but embrace it. Ceramics, once too brittle for aerospace use, are now being engineered into flexible, lightweight structures that can handle multiple flights without degradation. This evolution in material design isn't just about durability, it's about enabling reusability. If an aircraft melts or delaminates every time it flies, it becomes a missile, not a vehicle. But if it survives, if it returns intact and ready for the next mission, hypersonic flight enters a whole new realm, one where it's economical, repeatable, and ultimately scalable. Even the skin of the aircraft becomes part of the innovation. Multi-layered structures with active cooling channels, heat-dispersing tiles, and smart coatings are all part of the puzzle. At these speeds, every inch of the vehicle must function with surgical precision, or it fails spectacularly. As Hermes continues to test and refine these materials in its Quarterhorse prototypes, it's also laying the groundwork for its long-term passenger jet goals. Because the secret to turning hypersonic dreams into practical tools doesn't lie only in engines. It lies in mastering the fire. Cutting costs with 3D printing and innovation. Speed in the sky must be matched by speed on the ground, and nowhere is that more evident than in how Hermes builds its aircraft. While legacy aerospace giants often take years and billions to develop new airframes, Hermes is proving there's another way. By embracing advanced additive manufacturing, better known as industrial 3D printing, it's slashing costs, shrinking timelines, and rewriting the rules of aerospace production. Using Velo 3D's Sapphire printers, Hermes has begun crafting critical parts from high-performance nickel-chromium alloys that can endure the extreme heat and pressure of hypersonic flight. These printers don't just produce simple components. They can create intricate, hollow geometries that would be impossible with traditional machining. That means stronger parts, lighter weight, and less material waste. But the real advantage lies in iteration. Where traditional programs can take months to redesign and remanufacture a single part, Hermes can go from digital model to functional prototype in days. That agility allows it to test more often, learn faster, and evolve its designs at breakneck speed. The Quarterhorse MK0, MK1, and upcoming MK2 models are direct beneficiaries of this approach. It's not just a manufacturing revolution, it's a strategic one. By proving that advanced aircraft can be built affordably and rapidly, Hermes threatens to disrupt the aerospace status quo. Programs that once seemed out of reach for smaller players are now within grasp. And for the US military, it signals a new path forward, one where innovation doesn't require endless funding, but smarter execution. In the race for hypersonic supremacy, the winner won't just be the fastest, it will be the most adaptable. And Hermes is showing that with the right tools, speed and precision can coexist on the production line, not just in the air. The Pratt & Whitney F-100 engine upgrade. Behind every breakthrough aircraft is a heart of roaring metal, and in the case of Hermes's MK2, that heart comes from a trusted legacy, the Pratt & Whitney F-100 engine. Known for powering the F-15 Eagle and F-16 Falcon, the F-100 has already proven itself across decades of US military dominance. But now it's being brought into a new era. Choosing this engine for the MK2 isn't just a nod to reliability. It's a strategic bridge between the known and the unknown. While many hypersonic efforts rely on experimental propulsion systems, Hermes is blending bleeding-edge design with battlefield-tested machinery. The result? A prototype that doesn't just exist in theory, but in real, tangible flight capability. The MK2 will be the first Quarterhorse to move beyond taxi tests into full supersonic and potentially autonomous flight. The F-100 provides the thrust necessary to bridge from subsonic to transonic speeds, a critical phase for initiating scramjet propulsion or transitioning to hybrid systems. And its known maintenance profile makes it ideal for repeated tests without massive overhaul delays. But it's not just about what the engine does, it's what it represents. The inclusion of the F-100 signals a shift in Hermes's goals, from prototype demonstrations to operational readiness, from lab curiosity to battlefield tool. As future variants of the aircraft evolve to include next-gen propulsion, possibly Chimera or full scramjets, the F-100 lays the foundation for safe, controllable, repeatable testing. In short, it's the perfect workhorse for a future built at light speed. The secret test base and the flight deck system, hypersonic technology, demands secrecy, mobility, and resilience. And Hermes has answered that challenge with a radical new concept, the flight deck. On the outside, it looks like a shipping container. Inside, it's something far more advanced, a self-contained off-grid flight operations center capable of supporting high-risk test missions from virtually anywhere on Earth. This modular HQ is climate-controlled, AI-integrated, and equipped with all the infrastructure needed to command a flight without relying on traditional bases or support systems. In conflict zones or remote regions, where traditional airfields are vulnerable or non-existent, The flight deck can be dropped in, powered up, and made mission-ready within hours. It's more than a mobile command center. It's a force multiplier. By taking operations off-grid, Hermes can test at undisclosed locations, avoid surveillance, and operate beyond the constraints of fixed logistics. The system is also designed to be modular, allowing teams to scale up with additional units or adapt to evolving mission needs. Redundancy, security, and adaptability are built in from day one. And as future aircraft grow more autonomous, the flight deck will likely serve as a digital flight director, an AI tower guiding these next-gen planes through launch, flight, and recovery phases with minimal human oversight. This kind of forward-thinking infrastructure shows that Hermes isn't just building aircraft, it's building an ecosystem. A full-spectrum, hypersonic capability that includes everything from propulsion to operations to recovery. And in doing so, it's redefining what an Air Force base can be in the 21st century. Meet the Hypersonic, the future of global travel. While military dominance has been the driving force behind hypersonic development, the implications go far beyond defense. Hermes' boldest vision lies in a civilian marvel, the Hypersonic. Designed to be the world's first hypersonic passenger jet, Halcyon could turn transoceanic travel into a matter of minutes, not hours. Imagine boarding a flight in New York and landing in Tokyo in under 2 hours. No jet lag, no layovers, just seamless, stratospheric travel that makes the world feel dramatically smaller. But this dream isn't based on fantasy, it's grounded in the technology being tested right now. Lessons learned from Quarterhorse Mk2 and Mk3, including propulsion behavior, thermal shielding, and AI-controlled flight systems, are feeding directly into the Halcyon's design. If those aircraft prove the platform works, the leap to commercial application becomes a matter of certification, not speculation. The Halcyon's success would be a seismic shift in global connectivity. Business, diplomacy, emergency response, even tourism, everything would accelerate. The strategic and economic advantage for the US would be immense, essentially owning the next frontier of global commerce. And with sustainability in mind, Hermes is also exploring how to make Halcyon run on synthetic fuels or incorporate cleaner Scramjet technology, helping address environmental concerns that often dog supersonic travel. This isn't Concorde 2.0, it's something entirely new. And if Hermes delivers, it won't just be a new chapter in aviation, it'll be a new book. What this means for the world. In a world increasingly shaped by speed, connectivity, and technological supremacy, hypersonic innovation isn't just an engineering feat, it's a geopolitical earthquake. The United States, long seen as losing ground to rivals like China and Russia in next-gen aerospace, is rapidly turning the tide with companies like Hermes leading the charge. This new wave of American aerospace dominance is different. It's not driven by bloated budgets or decade-long programs, but by agility, iteration, and bold engineering. If Quarterhorse succeeds, if Chimera performs, and if Halcyon becomes reality, we'll be looking at a complete transformation in how nations move, fight, trade, and connect. The strategic implications are profound. From strike capability to surveillance, from executive transport to global rescue missions, the applications are limitless. And with mobile operations, 3D printed parts, and AI-guided systems, the barriers to global reach are crumbling. We are witnessing the early moments of a revolution, not just in flight, but in how power is projected and how civilization connects. Darkstar isn't just a machine, it's a milestone, and the world better be ready when it takes off.